At the worst possible moment. Okay.
Hello, everybody, and welcome to this hack-on session with Socrates Katsikas. If you have questions, you can use the chat functionality or the Q&A, and you will get answered either during the presentation or at the end. The stage is yours, Socrates.
Thank you very much for the introduction. I regret that I will be presenting in English. Jeg kan norsk, men bare litt. So it will be more difficult for you if I try to give the presentation in norsk. Please feel free to interrupt me and ask questions. Let's do the session as much interactive as possible. And let me also let you know that if you, of course, the video will be available, but if you want the slides in PowerPoint or PDF format, then you just ask me by sending an email to my email address, which is there. Let me just say who I am. Well, of course, my name is Socrates Katsikas. I'm a professor with the Norwegian University of Science and Technology, NTNU, in Gjøvik, the Department of Information Security and Communication Technology. And I'm also the director of the SFI Norwegian Center for Cybersecurity in Critical Sectors, or NORCIX for short, for which I will give you some more information towards the end of the presentation today. So, time to start. The agenda for today, and usually I'm very optimistic. I will see whether I will manage to go through the full agenda or whether we will have to take some shortcuts at some points. So, a few words about IT and OT integration within the context of the Industry 4.0 digital transformation of industry. Then cybersecurity challenges that arise because of this integration and the distinctive characteristics that these systems have. A way to systematize knowledge in cybersecurity, which is the NIST framework for improving critical infrastructure cybersecurity. How to apply this framework in the case of integrated IT and OT systems. Then we'll discuss a little bit about experimental cybersecurity, because this is one of the needs that comes up when we study the security of IT and OT integrated systems. And finally, as I already said, a few words about the SFI NORCIX. So, starting from the context in which we are looking at IT and OT integrated systems, this is, of course, the evolution of industrial revolutions since Industry 1.0, a couple of centuries back, until today's Industry 4.0, which, of course, is a term that has been devised by, or has been coined by Germans to describe this digital transformation of industry, whose main characteristics are the use of cyber physical systems, the Internet of Things, and of networks, of course. And of course, it is happening already today. It's there for some years now. Let me just tell you that I'm using now the full screen, so I cannot really read the chat. So if you want to ask a question, you can just speak up. Don't feel shy. When you put together or you integrate IT with OT, this is resulting in what we call an industrial Internet of Things system. Of course, there are different terms that can be used to describe such a situation, and we use IIoT systems, we use ICS or industrial control systems, we use the term cyber physical systems, and so on. These are not exactly the same, but of course they do describe things that are quite similar, or concepts that are quite similar. And because we will be using the other concept as well, of the term cyber physical system, on the right hand side of the slide, you can see the conceptual drawing of a cyber physical system. So what it does, of course, it is a system which relies on a physical state. It actually monitors the physical state, but it also acts upon a physical state. And then there is a cyber part which decides what kind of action should be effected based on the information that it receives from the physical component. Uh, the human element here is quite disproportional, but it is intentionally so because there is a common misunderstanding that cybersecurity or information security uh, is a technology matter. It's not. It is a multidisciplinary, or maybe I should say interdisciplinary matter, and the human element is very important in whatever we do about cybersecurity. Now, these cyber physical systems come into devices, which is possibly the smallest element that you can imagine. Uh, that can be an embedded system, for example. And then these devices make up systems when they connect to each other. And these systems may even connect to other systems, and therefore we end up having what we call system of systems. Now, all this uh, complexity or the scalability of these devices is one of the characteristics that makes them difficult to secure, and therefore the domain or the field of cybersecurity of cyber physical systems or of integrated IT and OT systems is something that is quite distinct from security in what we call traditional IT environments. So keep in mind this conceptual design for the rest of our discussion today. Now, this integration of IT and OT, by the way, this is a slight digression here. People sometimes talk about IT and OT convergence. It's actually not a convergence. These two are not converging, they're being integrated. So, close digression now. This is something that has been studied, it has been mentioned, it has been used for quite some time. In fact, the ISA 95 standard for representing such integrated IT and OT systems in the domain of manufacturing exists since 1995, so it's quite a long time. But it has not been used in the context of cybersecurity. So this is what is usually called the Purdue model of such systems, which, as you can see in the slide, is a layered model, starting from level 0, which is the actual process. This particular one is for manufacturing, but it can be applied to other industrial sectors as well, and goes up to layer 5, which today what we know as the cloud elements. And in between, of course, you can see all the other different levels that this model uses to describe IT and OT integrated systems. Now, unfortunately, the manner we've selected to present does not allow for animation. Otherwise, you would not be seeing immediately this little devil here or the arrows there. But I guess you can understand what the intent is here to show that unfortunately we're not living in a world with angels. So there do exist adversaries outside the system and also inside the system that would like to launch attacks against them. And this is, of course, why the need for cybersecurity arises. Now, what is special, just to start discussing, what are the special characteristics of these systems as opposed to traditional IT systems? Well, there's this level 0 and even the level 1 of this model was never designed to be secure against cyber attacks. The reason being that the underlying assumption has always been that this manufacturing process and the equipment would be physically and logically alone, not being accessible from outside of the factory or the shop floor itself. But Of course, in our infinite wisdom and in order to improve productivity and so on, let me not go into a discussion of discussing all the advantages of this Industry 4.0 or the digital transformation. We made this inherently insecure platforms uh, accessible in practice through the internet. And so an adversary now is possible to has the capability to go through uh, this path uh, and actually attack the physical processes underlying the whole model, because simply accessibility through the internet is possible. The stars indicate possible points of attack, but we will come to this later on again, so I will not spend more time on these attacks. But the key take away from this discussion up till now is that, of course, it is possible to launch cyber attacks against these integrated IT and OT systems because of their connectivity to the outside world and because they had not been intended to be designed as secure systems in the first place. Now, a reasonable question would be, fine, we do have a cybersecurity problem with these systems. Why can't we simply port solutions that we have developed for IT systems into the IT and OT domain, and that's it? And then there is no case to discuss. Well, there is a number of distinctive characteristics that such systems have, which make them quite different from a security point of view from IT alone or IT traditional systems. And therefore, there is a need for looking at cybersecurity in a different, of these systems in a different way. And I will not go into detail in this list. The intention is to give you an idea of how long the list is, and I will just pick a few of these characteristics to give you more insight into this. We have already discussed the interaction with the physical world as one of the characteristics of such systems, but of course, IT systems do not have. And because of this interaction, there is an additional element that these systems have to be satisfying, additional requirement, and this namely is safety, of course. Whatever interacts with the physical world should be also safe for humans, for the environment, and so on. We also discussed in the conceptual model of cyber-physical systems, these systems of systems nature, which practically means that something that is designed as a standalone system may find itself as a member of a federation of systems, and therefore the behavior that it may exhibit in such a situation may be unpredictable, and sometimes is, which means, of course, that there are repercussions on the cybersecurity behavior of the overall federated system. Then another important characteristic is that such systems are usually time aware and deadline sensitive processes. So you can't simply say, oh, well, we'll bring it down if we find the vulnerability, we'll bring the system down, take a few hours to patch it, and then bring it up again. Simply, this doesn't work. And of course, even the controls that we need to apply have to be aware of the fact that time is of importance. And this, again, for example, rules out the use of conventional encryption because this is too time consuming in such settings. The complexity of the supply chain is something that is quite prominent now in discussions about cybersecurity. The truth is that unfortunately we don't know how to deal with fully with cybersecurity in the supply chain. This is an open issue, and in fact, it is also an open issue not only for research but also for regulation and for legislation and so on. And also a very important thing that is very often overlooked, particularly in research environments, is the problem with legacy industrial control systems. Usually in research, we concern ourselves with the future, but the truth is that in industry, in the real world, And particularly in critical sectors, there are industrial control systems or components of industrial control systems that have a lifetime expectation which exceeds by far the lifetime expectation of any IT, including cybersecurity products and solutions. So, for example, you would find in the power domain equipment whose lifetime expectancy is 30 or 40 years, sometimes even longer. So it is not realistic to come up with cybersecurity solutions that only look in the future, but we should be looking also at the problem of securing legacy systems that are not even aware of what the IP, protocol stack is, for example. Of course, they are all resource constrained usually, so no way of applying solutions that require high computational capabilities, and the requirement for always on is also important, so we cannot really afford downtime. But as I said, just to give you an idea of some of these characteristics, and you can go on and think about more of those at your own time. But again, the message here is, well, we can't really simply use the arsenal of solutions that we have already developed for securing IT systems in the IT and OT integrated systems domain. So, just to reinforce this argument, out of the discussion of these characteristics, what actually has come up as a conclusion, as one of the conclusions, is that, and this is actually the underlying root reason why we cannot use existing solutions as they are, is because the CIA model, confidentiality, integrity, availability model, is simply not enough for IT and OT systems. And the extension of the model uh, has been extensions to the model have been proposed. I think that possibly the most prominent or most widely accepted one is the enhancement of the model by principles by or attributes coming from control systems theory, namely controllability and observability, and an additional attribute which is called operability. Other models also include maintainability, resilience, and so on and so forth. But again, the main idea here is that CIA is not enough for securing uh, IT and OT integrated systems or cyber physical systems or IIoT systems, whatever you prefer, whatever term you prefer to use. And this again brings us to the need to develop or to look at the cybersecurity of such systems in a different way. How can we do that in a structured way? Well, the NIST cybersecurity framework was originally designed and devised so as to help the United States critical infrastructure operators to improve the cybersecurity of their systems. Uh, it has been used since it originally appeared several years ago, not too long. I believe it's about less than 10 years. It has been used for several purposes and in different sectors to guide this process of improving the cybersecurity. So not only for critical infrastructures, but in other sectors as well. Now here I use it only as a way to uh, systematize the way we look at the cybersecurity of the systems in question, so cyber physical systems. Uh, so, a few words about the framework. It essentially defines five core functions, as they are called in the model. You can also think of them as five phases in the lifetime of a cybersecurity project. And these are the identify function, the protect function, detect function, the respond function, and the recover function. So each one of them is supposed to give answers to questions which you can see right below the respective column with the core function. So the first one, identify function, is supposed to give answer to the question what processes and assets need protection. And you can see within its detailed description items that need to be looked upon within this core function. And then when we go to protect, of course, is now that we know what we need to protect, is what control should we put in place so that we can achieve the protection of those assets that we want to protect. Then comes the detect function, which answers the question what techniques should we have so that we can identify incidents. Now here is an interesting point. Of course, we've always been looking at ways for detecting attacks, but the doctrine we're using in cybersecurity, and in particular in such systems now for some time, has changed since the past. In the past, we were trying to build systems that would be secure. And we were talking about concepts like security perimeter and how to keep the bad guys out and so on. Well, we now know that this is not enough. We know that there will be attacks against those systems. And we also know that these attacks, some of these attacks, will be successful. And therefore, we not only need to have ways of detecting that an attack is going on, which is not always trivial. Just keep in mind the advanced persistent threats or APTs that can be there for a couple of years before we can actually detect that they are there. And not only we will be attacked, but we will be successfully attacked. And this means that we need ways to contain the impact of the attack or the incident. And this is what the response function does. And even more, we will be successfully attacked to an extent that we will need to lose some of the functionality of our systems, and therefore we will need to recover. And this is what the last core function in the NIST model does, answers the question what techniques can restore our capabilities. So, using this as a framework for systematizing the field or the area of cybersecurity in IT and OT systems, let me start with the identify function, which mostly is centered around risk assessment. And of course, one way of describing risk assessment itself is by using the ISO 27005 model for risk management and assessment. Of course, these comprises these two elements: the identification and estimation, and then of course the risk evaluation. So why not use any of those dozens of risk assessment, risk management methods that exist in the market for IT systems and just use them for IT and OT systems or for CPS systems? Well, the answer lies in what I said before about the inadequacy of the CIA model to handle the cybersecurity of such systems. And therefore, we need to come up with new methods that are specifically designed to analyze risk in CPS environments. It turns out that in the absence of anything better for now, the most widely used method in industry for such systems is STRIDE, which is quite surprising, as STRIDE itself has been withdrawn by Microsoft as a method for analyzing risk and threats, actually, in traditional IT systems. But this is the way things are. And STRIDE actually looks at those six types of threats and how these map to the security properties of authentication, integrity, non-repudiation, confidentiality, availability, and authorization, and analyzes the environment using this kind of philosophy there. Of course, as it stands by itself, is not enough. It's not adequate, sufficient enough to cover the whole process of risk assessment, particularly in CPSs. And therefore, it is good to use it together with another Microsoft-based method, which was called RED, which allows you to assess the impact of any particular possible incident in a system. So those two together can give a good indication of the risk landscape in IT and OT systems. Some of these modifications have been developed by our own research group at NTNU. Of course, there are other approaches as well. And this is just one example of how this modified STRIDE method that we have come up with applies to the case of cyber-enabled ship. Not necessarily fully autonomous, but also remotely controlled. And the slide is only an indication of how this works and what the results are. Now, remember also that one of the distinctive characteristics of CPS is that they connect to each other and they create federated, sometimes, systems of systems, which means that we need also to have some way of analyzing how the risk propagates in such situations. So even if we have analyzed the risk of one component of the system or of the system, when this system becomes part of another larger system, how does the risks of the first system propagate into the whole? And again, this is something that we have been doing work on in NTNU with some useful results, trying to answer the overall question: can we somehow assess the risk of an overall system by reusing the results of risk assessments of its individual components? And it seems that we are on a good path towards answering this in a way which is also practically useful, besides being theoretically interesting. In the same line of thought, this is again some work that we've been doing at NTNU, because it supports this risk propagation idea. You need to identify dependent components in cyber-physical systems, and we've been using, of course, graph techniques to analyze such systems and come up with the identification of dependent paths in the system, but also critical nodes and attack paths, because of course attacks are expected to be launched against the most critical or the most vulnerable nodes in the system. Then, to complete the discussion on the identifying function, of course, one needs to do the risk assessment, the risk evaluation, so as to come up with the security requirements. And there are methods for doing that for IT systems, but not many for IT/OT or CPS systems. So one of these we came up with again in the group. It's a method for eliciting security requirements for cyber-physical systems, and also we extended this to elicit both safety and security requirements at the same time. The main difficulty with doing that, because there are of course other methods for doing this, but the main difficulty is that if you do these two requirements elicitations separately or in parallel, not integrated, what you end up with are sometimes, more often than not, conflicting requirements, which we then have to resolve. And this means that you have to go back in the analysis and re-elicit the requirements and so on. So with our proposal, fortunately, we can do this in an integrated way, and therefore we just do not have conflicting requirements, simply because this has been taken care of in from the original design of the method. And then after having elicited requirements, of course, one comes up with the question: okay, what are then the security controls or the countermeasures that we should apply so that we satisfy the requirements? And again, of course, there are many methods that give an answer to this, but there is no unique answer to this question. In fact, we usually come up with different options for cybersecurity controls to be applied to mitigate a specific risk. So what we looked also into is how can we optimally select such countermeasures. And again, there is work on traditional IT systems about this optimality question, but usually it focuses on the question, what kind of controls should I select within a limited budget? Well, we extended this question, and we actually tried to find answers, and we did, to the question, what are the optimal controls in the face of a specified budget, and at the same time, a desired residual risk situation. So actually, to minimize also the risk as well, or to optimize jointly the risk reduction and the budget utilization. Now, coming to the protect function, again, the motivation. We've been talking about the need to look at security and safety for IT/OT or CPS systems at the same time or jointly. But then, of course, a reasonable question is, but wait a minute, in all these systems, particularly those in critical sectors that are usually highly regulated, they do have a lot of safety requirements and safety measures that are in place. And of course, cybersecurity eventually in such systems may result in a breach of the safety of the system. So why don't we use all these measures that are already in place for securing the safety of a system, and which of course they follow a defense in depth model, and we need to come up with new measures? Well, the answer is that safety is usually looked upon under the assumption that we will have statistically independent events that may influence or may affect adversely the safety of our system. And this assumption simply does not hold in the face of an adversarial cyber attack. So this is the primary, or if you wish, the philosophical or the root cause reason why we need to again take a look at these measures from a different viewpoint. And of course, this is just a list. I will not go through it of protection measures that have been proposed and are in the literature and are available for protecting CPS systems. I will just draw your attention to this bullet point, these bullet points here, that one size fits all approach is not efficient usually, even though there are products in the market, of course, that they would promise that they will secure your CPSs most efficiently. The very popular countermeasure of encryption, as I already hinted at the beginning of the talk, doesn't work because mostly of time requirements. So we have to come up with lightweight and flexible encryption algorithms. And finally, what is also interesting, also from a research point of view, is the use of blockchain technology for securing IT and OT systems. And in fact, we've done some work on that also at NTNU for using blockchain for ensuring the authentication and the authenticity of devices that take part in an IIoT network. But this is a good point to start discussing attacks, because that's what detection, of course, is all about. So the next function here, and this is a simplified schematic of what an industrial control system or a CPS looks like. So I think it's self-explanatory. I don't need to explain what this is. It's just redrawing this conceptual model that we had at the beginning. But the numbers in the red circles actually represent points where we can have attacks against such a system. And surprisingly, there are quite many. In fact, all of the elements in such a system can be attacked in a way or another. And this is not theory. We have experimentally confirmed the possibility of such attacks in many cases. Uh, so now coming to a more detailed look at these attacks and also classification of their importance. This is from an ENISA report. ENISA is the European Union Agency for Cybersecurity, and in a report about the security of Internet of Things within smart manufacturing, uh, they came up with this classification and attribution of the severity of attacks against such systems. Even though the report is a few years old, it is still applicable. I think that the threat landscape, as published by several cybersecurity companies around the world, does not deviate too much from that. And of course, this only verifies the fact that we can have different types of attacks against such systems at the different points that the previous slide showed to be possible. Now, a particular attack scenario, which is, I think, from the same ENISA report as well. But the interesting thing about it is that this corresponds to a real attack that has happened. Of course, it's not named specifically, but it's a real attack. So the scenario was this. There is an industrial robot in an Industry 4.0 environment, and the attack was about manipulating calibration parameters of the on which the robot was using to do its work. Of course, this attack targets the sensor processing and the knowledge model levels of the control system underlying this situation. So, in some more detail, and again, hopefully to increase the insight of how these things work. Uh, Remember that there is an industrial robot which is connected to a controller. The programmer uploads code to the server, and then the sensing equipment is calibrated. And the calibration data initially are stored in the sensing environment, and then they are transmitted to the controller, which uses the local copy of those calibration data. Now, the attacker may tamper with these calibrating parameters, because of course it is possible to reach these storage areas from the outside, and therefore original and unmodified code is executed. So there is nothing wrong with the code, but the calibration parameters are changed, and therefore the result is that the robot moves erratically or unexpectedly. Now, the impact of such an attack, you realize that can be quite high. Is it easy to detect? Well, yes. Once it has happened, yes, because the human operator will notice it, but by then it may be too late. So we do need to have ways of detecting such kinds of attacks earlier on. And this is a list of intrusion detection systems that have been proposed for such systems. I just will talk a little bit about this particular case, because the others have been used also in IT traditional settings, but the physics-based or process-aware IDS is something that is only applicable to such systems, and therefore it deserves some more attention here. Just on the site, of course, you know how machine learning and AI are very popular today, and we are bombarded by the messages that these will solve all our cybersecurity problems, or hopefully they will. This slide would better be animated, but unfortunately this is not the case. So I'm just bringing it up so as to somehow fire a discussion about the efficiency of such techniques in intrusion detection. And this is an experiment done a couple of years ago. It's a well-known scenario and a well-known experiment. Several machine learning based classifiers were used to identify what this image is. And of course, with 88% certainty, they came up with the conclusion that it is a tabby cat. And then this image was a little bit perturbed, adversarially perturbed, with the result being this one, which of course visually, I'm sure you cannot say that it is very different from this one. But the ML-based classifiers decided with 99% confidence that this is not a tabby cat, but a guacamole. So you can imagine with this kind of behavior, why coming up with safe and secure AI, particularly when we decide to use it in cybersecurity, is really paramount today. So, what is not so susceptible to adversarial attacks as intrusion detection method is what we call the physics-based attack detection, which the underlying assumption here is that, well, why don't use the knowledge we have about the physics of the process that this control system controls to decide whether there is an attack going on or not. And there are several ways of doing that. This is the conceptual model, that we build a physical model of the process that we control, and then the concept is that we look at the actual measurements that we have and what the expected measurements should have been, and if there is any difference there, then we raise an alarm about an anomaly detected there. I'll use the last 4 minutes to just give you an idea of work that we are doing now at NTNU, which is motivated. Don't use the code, please. I mean, this we don't have time for that. This is just to motivate the discussion. And the hint here is that unless you have the possibility to systematically experiment, then we cannot talk about science. And in order to experiment with cybersecurity in IT/OT systems, we need to have test beds of such systems with hardware in the loop that can realistically represent such environments, because of course you realize that it's not a good idea to start experimenting with real systems. This is some work that we did several years ago, 4 years ago, I believe, about the how such test beds should look like, and we came up with a reference architecture. Now, you probably know the Norwegian Cyber Range, which is a traditional IT cyber range that we host at NTNU. So what we are now doing to put the two together is we are moving towards the next generation of the Norwegian Cyber Range, which we call this Norwegian Cyber Physical Range, which uses, of course, as the base the existing NCR, but connects it or links it to a number of test beds that are geographically distributed, by the way, of physical systems, so that we can come up with an environment in which to experiment with the cybersecurity of such cyber-physical systems. And this is one of the tasks that we are looking into within the context of the NORCIX SFI, which is the research-based innovation center. We started operating in October 2020, so it's a little bit over 1 year of operation. We have funding for 8 years, so until the end of 2028. The funding comes from the Research Council of Norway and from the participating industry. And you can see the parts of NORCIX here. As you can see, there are several sectors that are represented, and also a number of international collaborators that are universities and research centers of high standing around the world. The work we do in NORCIX has 4 focus areas that have been agreed upon with our industry partners as being of primary interest with regards to cybersecurity and the digital transformation of industry. And these are, of course, the IT and OT integration issues that we discussed today. The second one is about the use of 5G in the digital transformation of industry and what cybersecurity issues arise because of that. Human and organizational aspects, remember that these are very significant in this digital transformation. And finally, the use of data analytics for cybersecurity in the digital transformation of industry. So to conclude, we do get serious security challenges because of this integration, not convergence. We cannot use simply security solutions from IT to port them into this domain. They will not work. Securing legacy systems is equally important with the future. We have a lot of open research problems. Some of them are, maybe all of them to me look exciting. I hope Maybe some will look exciting to you as well. And for professionals, I don't know if this is good or bad news, but this insecurity situation is likely to continue for some time because we simply cannot be solving all these problems so soon. So this is our Nordics motto, and this concludes my presentation at this time. Thank you very much for your attention.
Thank you, Socrates. There are no questions, so that means that this is the end of this session. Thank you for guiding us through this, Socrates, and thank you for watching the presentation.
Thank you very much. And if there are any questions, I'll be happy to take